In this video, we're going to talk about something that has to do with leveling, and that is the Earth's curvature has an effect on leveling. So we've talked about in the past the fact that when we're talking about horizontal distance measurement, how it's important that, if you're going to do long distances, you have to do all of these corrections, and there's only a certain amount of distance to which you can measure without really having to worry about the curvature of the Earth. But what if you do have to worry about the curvature of the Earth? Now, there's lots of things that that happen when you're looking at ridiculously long distances, and we're not going to look at them here. We're still within plane surveying field. However, there is a small correction that can be negligible in most situations, but can become more substantial as you're measuring longer and longer distances because of two things. One is the atmospheric refraction. So what's atmospheric refraction? And curvature of the Earth. So these two are affecting how we take measurements. So let's look over here. So let's say we have here Earth's surface, right? And we have a horizontal line. So if you're measuring from here to here, and of course think about this, this is like a humongous distance right here. But as you start seeing, you see horizontally, and there is going to be a difference between where the Earth actually is and where you're measuring to. So if you had somebody, standing here with a stick and someone standing here with a stick, you may be reading it here thinking that it's only this high, but then there's huge correction. Now, of course, you really can't see someone standing over here. They would disappear, but I'm just trying to make an example. So it's very small, but of course, as you get further, it gets larger. So C stands for correction, and we're going to, the same way that we did a correction for the different factors that affect the way we tape, the way we do chaining, then we're going to do the same with leveling. So you're going to read your, you're going to read your level wrong if you pass a certain point, and we're going to talk about how to fix that. In most situations, again, you won't have to worry about this. On the other hand, you have that's a hard word to say for me for whatever reason. It's atmospheric refraction. So atmospheric refraction does the opposite. The correction is in the opposite direction. So in a way, it's the way the light bounces and kind of gives you this fake impression that things are straight in front of you when they're not. So between this correction and that correction, we come up with this number right here. So if you want to figure out how did that number came to be, there's actually a pretty easy derivation for this, and it has to do with just basic math, right? So if we have here a triangle, right? So we have D, C plus E is one side, and E is the other side. So really, let's look at it this way. Where this is E plus C, this is E, and this is D. Then with Pythagorean theorem, we come up with the fact that D squared plus E squared is equal to E plus C squared, right? Okay, so we can actually make this a little bit of math. And we would have that with a little bit of math. D squared plus E squared is equal to E squared plus 2EC plus C squared, squared. But this last term, we're going to make it go away because it's going to end up, so when you're leveling, the maximum sight distance is probably only a few hundred feet and no more than a few miles. So for such distances, this value of C, which is that correction, is going to be so tiny that, when you square it, it's really going to kind of go away. So let's make that go away. Just trust me. After which, you can actually, in this, we're going to try to solve for C. And I really should have left more room. So from here, I'm going to come over here. So if I solve for C, C is equal to D squared over 2E. And we know that E, the average radius of the Earth, is actually 3,959 miles. So this is D squared over 2 times 3,959 miles, which, if we solve this, gives me let's see, 0.0001263 d squared, oopsie. And then if we want to convert this to feet, we can multiply that times 5280. So we end up with C is equal to 0.667 d squared. And that is only to account for the curvature. So for this. On the other hand, we're going to find that there's a variation in refraction of 0.093 feet per 1 mile, but it's in the opposite direction, so the corrections goes in, like, it has the opposite sign. So if we do that, so 0.667 minus 0.093 is equal to this 0.574. I know I just went really, and then we can replace d with m as in miles, so m squared. That's where that came from. If that didn't make any sense, I went too fast, or I just started kind of rambling, please read it in your book. There's a step by step. So in any case, all that you will need to know is that if you have, for example, a telescope reading on a rod that's 100 feet away, you just this has to be in miles, right? So you have to convert feet to miles. So it would be, let's say, 100 feet away. That would be 0.574 times 100 over 55280 squared, and that gives me a correction of 0.000206 feet. So you see that for 100 feet, really the correction's so tiny, we don't get till the 10,000ths place. So you are good. But let's do a couple of examples. Example A says, compute the combined effect of the Earth's curvature and atmospheric refraction for distances of 100 feet, which we just did, 250 feet, 500 feet, and 3,000 feet. So all we need to do is what we just did. So for 100 feet, it would be 0.574 times 100 over 5280 squared, which is equal to 0.000206 feet. This is the error, right? If we have 250, 0.574 times 250 over 5280 squared equals, I actually don't have this number, so I'm going to plug it into my calculator, but feel free to do it yourself. Same thing with 500, same thing with 3,000. Now when it's 10 miles, watch out, you don't have to convert. This is already in miles, and you will see how a number that starts off being super insignificant becomes a lot more important as the distance gets longer, of course. All right. So the next one says, a backside of 5.43 feet is taken on a level rod at a 120 feet distance, and a foresight of 8.26 is taken on the rod held 1,100 feet away. What is the error caused by the Earth's curvature and atmospheric refraction? What is the correct difference in elevation between these 2 points? So for 120 feet, we have this correction, which is C is equal to the 0.574 times 120 over 5280 squared, which is equal to 0.0003. For the 1,100 feet, this is C is equal to 0.574, 1,100 over 5280 squared. This is 0.0249. So the total error is 0.0003 minus 0.0249. So this is negative 0.0246 feet. So the correct difference, let me write it down. The correct difference in elevation between the 2 points is going to be 5.43 minus 0.0003 is equal to 8.76 minus 0.0249, which is equal to negative 3.3054. Okay? Does that make sense? So it starts something that, maybe didn't matter much. At the end, well, this is not an equal, this is minus. I'm misreading my notes. I'm sorry. Ends up actually making somewhat of a difference. Okay. That's it for this topic. And we'll continue with the next video.